Okay, so making progress, almost done. Hard to believe it. Today, last time we did group theory for COs. What makes something undergo linear absorption of a photon? What does that mean?
Antisymmetric vibrational mode.
Antisymmetric vibrational modes absorb photons in a linear fashion. And why is that? It has a transition dipole moment. You push charge around with that electric field because excitation couples to the oscillating field of the photon. Okay, so a dipole moment develops when you stretch. That happens when the motion, the normal mode, has X, Y, or Z symmetry. So you look at a character, you figure out, you do the reducible representation, break it into irreducible representations, where the basis function is the stretching, and then you check and see if X, Y, or Z appears in the irreducibles, right? Complexes that have dipole moments tend to have vibrational modes that are IR active. Any motion is dipolar if the compound has a dipole moment, as long as the stretch is aligned with the dipole moment. Okay. We did some chemistry with COs. One of the ways you get a CO to fall off is you shine light on it. You can do nucleophilic addition to carbonyls, and then it's just sort of chemistry on the ligand. It's a little bit confusing, right? A little bit confusing because you make acyls all of a sudden, but it used to be this thing we treat as an L-type ligand. We treat it like an L-type ligand because of the formal charges that we don't draw. And that gets kind of funky when you start adding a nucleophile to that carbon. So there's some sort of weird examples there. All right, so today we're going to keep talking about coordination compounds. I'm going to breeze through some stuff so we can get to the meat and potatoes next time. You guys you saw an isonitrile on your homework, an isocyanide or isonitrile. These are compounds that look like this, and they are isoelectronic with carbon monoxide, okay? How would you say they differ? They have the same sort of triply bonded resonance, carbon lone pair, minus on the carbon, plus on the nitrogen, minus on the carbon, plus on the oxygen. What's the difference between these two compounds in terms of their character?
Well, they're both removed from you ask, can I remove it from the R? Like if you take that away from the R, they won't be the same. That you'll have a cation and the alpha ion.
Well, I don't want you to break the thing apart. I just want you to tell me if I made a complex with this thing and I made a complex with this thing, how are they going to be sort of different from each other? This one is more electron deficient because the oxygen is electronegative, right? This is a better pi acceptor. This is a better sigma donor. This also brings this R group with it. You can put all kinds of spinach out here, and that has a big impact on the compound that you're talking about. Okay, so this guy has a dipole moment of 3.44 dBi. And this one has a dipole moment of 0.11 dBi. That tells you that there's a lot more negative charge buildup out here. All right, so they're weak pi acceptors and good sigma donors compared to carbon monoxide. You can make compounds like iron 2 hexaisocyanide and silver 1 tetraisocyanide. Those things are stable. You cannot make the tetracarbonyl. Or the hexacarbonyl or the tetracarbonyl of the same compounds. What does that tell you?
Does it mean that the one on the left with the isocyanide are only sigma bonding, and there's no reason for those two? Those are pi bonding. They want a pi bond, so they're not going to bond as well to the metal.
Yeah, that's exactly right. And this metal, silver 1, it's pretty good. It's a pretty electronegative, actually. Silver 1's a good oxidant. And it doesn't really buy back bonds, because you're talking about a filled D shell. Those are essentially core orbitals. You can make silver 2 and silver 3, but it's really, really unusual. Okay, it's usually getting into the D manifold is hard. So this is not much of a pi back bonder, and CO is not much of a sigma donor. So this thing falls apart. Same is true here. Iron's not a bad pi back bonder, but oh Jesus, sorry, I need a 6 there. Iron 2 is not a bad pi back bonder, but CO is not enough of a sigma bonder to hold that thing together. All right, so you can make isocyanide and CO complexes like chromium hexacarbonyl and chromium hexaisocyanide, nickel tetracarbonyl, nickel tetracyanide. Those things are perfectly fine. So it's not like you don't see, both in some metals. But they are different from each other. When you make a metal complex, put some lone pairs in here. You can 2 by back bonding, like this guy. And make stuff that looks like that. And so you might say, all right, well, that should be 120 degrees. Turns out it's often close to 180. You also often see this type of thing. If the metals are the right size, you form these sort of bridging examples. Here, the angle is more usually bent. And sometimes these are bent too. Okay. Sort of depends upon the compound. All right. So when it's bridging like this, there's a plane here that's defined by those 3 atoms. That helps this thing go away from 180 degrees. When you just have a terminal one like that, you have a pair of pi donating orbitals. So there's really no driving force to bend. Okay. All right, or less driving force to bend. What is the driving force to bend? Well, you might want to partition some of the electron density into an s orbital, like we learned about in Bent's rule. but it turns out that it doesn't bend very much. In this case, because there's a plane, the X and Y directions are very different from each other. All right, let's talk about dinitrogen. Lots of dinitrogen chemistry out there. Terminal N2 is pretty common. You see this sort of thing. And you can make the various resonance depictions that you might imagine. All right. So you can imagine that type of thing. And most of the time it's like this. Okay, this is often the best structure. N2 is nice and stable. This one is most important. N2 is a weaker sigma donor than carbon monoxide and a weaker pi donor also. So let's see here, the CO, the HOMO is that lone pair, right? The HOMO comes in at minus 14 electron volts. The N2 HOMO, same thing, minus 15.6 electron volts. So the fact that that number is larger, is more negative, implies the electrons are further from vacuum. It's harder to rip an electron off of N2 than carbon monoxide. So N2 is a weaker sigma donor than CO. I have the pi star. I have a note in my notes that I have these energies wrong for the pi star orbitals. I'm just going to write that N2 is a weaker pi back bonder. So for the same reasons, the pi star level on the N2 is going to be higher in energy than the CO1. So the empty orbitals are deeper, and that means that electrons will transfer into them more easily. So it's harder to do the pi donation to N2 than it is to CO. So N2 is kind of inert. It doesn't really want to participate in bonding. It's not really a strong donor. It's not really a strong acceptor. It's sort of lame as a ligand. All right. Now, despite the fact that it's a weaker pi back bonder, its bonding to transition metal centers is kind of dictated by that property. So it's primarily a pi acceptor in its coordinating ability. Let's see here. Here's an example complex. This trisisopropylphosphine, iridium chloride, forms an N2 complex. And the dissociation of the bond dissociation energy of the iridium N2 bond is greater than 36 kcals per mole. We can only get a lower limit for it, but it's about 36 kcals per mole, they estimate. And that's pretty weak, right? What's an OH bond? Or what's a CH bond worth? About 100. Some are weaker, some are stronger. It's about 100. That's a third of that, right? CH bonds are pretty strong. 36 isn't much. The NN vibrational frequency of this compound is 2331 wave numbers. No, I've got that wrong, sorry. It's 2105 wave numbers versus N2, where nu NN is 2331. Okay, so the vibrational frequency went pretty far down. That's a big change. Nu N2 for a transition metal complex is typically 1900 to 2100. Okay. It's also possible to measure, oh yeah, small point here. How do you measure this number? It's 2331. Liquid nitrogen? Probably not. No, that's probably room temperature. How would you do it? If I said, go measure the frequency of this thing, how would you do it?
Check IR, right?
Yeah, you check the IR, but you won't see anything. You go put N2 gas into an infrared spectrometer, nothing's going to happen. What? No frequency from crystallography. Why don't you see a signal on an FTIR? There's no dipole moment. The vibrational frequency has no transition dipole moment. Well, you could do some games like that, but that's not going to give you a dipole moment, really. Not much of one, anyway. What's another way you could measure that stretching frequency?
Can you do UV lit on it?
You could take an ultraviolet spectrum. That's not going to tell you the vibrational frequency.
You have to make some sort of dipole.
You put it in the field? I like that idea. There's another way to do it. You already know about it. What's the other vibrational spectroscopy we have briefly mentioned? Raman. You take a Raman spectrum of N2. There's only one vibrational mode. Okay, that's it. So this is a Raman frequency. Okay. There's also bridging N2. These types of things, people are very tempted to write this. That looks pretty good. Kind of interesting, right? This type of a bridging thing here is called mu2 1, 2. And the 1, 2 tells you that the 1 nitrogen and the 2 nitrogen are involved in making the bridge. Okay. And there's 2 metals to which those 2 atoms bridge. There's also this kind. It's a good one. This is called Sidon. mu2 1, 1, 2, 2. You get that right? 1, 1, 2, 2. You can imagine resonance structures here too, right? We've drawn resonance structures for alkenes binding metals. You have metallocyclopropanes. You can get metallocycle, I don't know what the hell you call that, hydrazine. All right, so there's a lot of N2 chemistry. Why is there a lot of N2 chemistry? There's a lot of N2 chemistry. A lot of inorganic chemists have tried to prove their mettle by doing N2 chemistry. Why does everybody care so much? There's this thing called the Haber-Bosch process. How many of you have heard about the Haber-Bosch process? Quite a few, not everybody. Haber-Bosch process is used to make fertilizer. Sorry. And basically you take hydrogen made from natural gas or coal or whatever, and you hydrogenate dinitrogen. I think 70% of our atmosphere is N2. You're swimming in it. You hydrogenate that and you get ammonia. And then the ammonia is used to feed plants. It's gasoline for plants. It's this interesting reaction where you take alumina and potassium oxide. So you make potassium aluminate of some kind. You mix that with some iron and you add a little bit of ruthenium. And you get this powder. You heat the hell out of it. (350 to 550 is pretty hot. We do chemistry at 350 degrees in our lab in hydrocarbon solvents. It's not like totally crazy, but that's pretty hot. And you add 500 atmospheres of pressure, of N2 and hydrogen pressure. 500 atmospheres is a lot of pressure. That's 7,000 PSI. So that's like taking a couple high pressure cylinders and combining them in one cylinder. Okay, so it's very high pressure. And that helps this reaction to go, which is almost thermoneutral. It's slightly downhill. Okay. So this thing has about the same chemical potential as this very stable gas and this extremely flammable fuel. You're taking all the energy here, right? You think about this as the source of the energy, I guess, because I imagine it relative to what it does with oxygen. This burns in oxygen, makes a wonderful boom. It's a good trick. You put it into this molecule. This is not really flammable, but the potential energy that's in here is consumed by plants, and they make tissues out of it. And then you eat them, and you get these nitrogen atoms in your own tissues. And it turns out, because this process doubles the world's food output, about 60% of the nitrogen atoms in your body have flown through a Haber-Bosch reactor, which is, I love this fact. I'm also terrified by it, because society is incredibly dependent on this reaction. And it's caused a huge population boom. You know, if you look at like world population and the discovery of this process, this is what made societies possible. Not the only thing, of course, but pretty important reaction. And it has these extreme conditions, and inorganic chemists say, hey, let's see if we could do this at room temperature, because this happens in the ground. Actually, there are organisms in the soil that live in these little rhizomes that plants borrow, and they make ammonia, you know, in the summertime in the dirt. So it's pretty easy to do for them. We have to do these extreme sorts of things. And so people have been trying to figure out how to do this in a more mild way for a long time. Yeah.
Are those being used as catalysts in
Yes.
that reaction? So they keep reusing, they keep the reaction.
Yep. What ends up happening is that the dinitrogen and these particles of metal react with each other. And the N2, the hard part is that it breaks in half on the metal, and you get metal nitrides. And those metal nitrides then get hydrogenated by H2 to make ammonia. And to break N2 in half and form metal nitrides requires this kind of temperature. Okay. So, yeah, there's a big push to do it electrochemically. If you could do it electrochemically, then you could do it in a distributed way. This is done in an oil refinery, and then it's shipped all over the world. You could do it electrochemically. A farmer could have a solar panel or a wind turbine and an electrochemical cell and make their own fertilizer. That's a nice picture. Okay, so I think that, I have all these wonderful slides about various example hydrogenation attempts. I want to show them to you, but we should move on because I think we should do other material. Oh, I'm gonna spend 15 minutes and I'm going to show you some classics maybe. Okay. So just a few. So the first N2 complex. Gotta do this one. If you take ruthenium trichloride, it's an H2O adduct. I think there's two of them. And you mix it with hydrazine in water. Hydrazine and ruthenium trichloride will react. And you can make this N2 adduct. This was in 1965. They made this compound and people sort of said, hey, this is really good news. We can make put N2 on ruthenium. We're going to be able to hydrogenate that sucker, and we're going to start making ammonia in these very simple ways. We don't need this crazy Haber-Bosch reaction. And since then, basically for the next 50 years or 60 years, people have been struggling to hydrogenate into a metal center. So while that compound is pretty easy to make, it is obtained in low yield. I should have noted that. It does not react with H2. Just typically what happens is that the N2 ligand just falls off. It sticks, but it also just kind of falls off. Talby demonstrated you could make the same compound in 1967 just by taking the pentamine aquo ruthenium 2 complex and adding dinitrogen to it. Let's see here. So it's interesting that water does not displace N2 off of the ruthenium center, but slightly stronger ligands like chloride will. Okay, 1969, Chat, who spent most of his life, I think, one of his main things was trying to hydrogenate N2. He has one of the only or early examples of N2 hydrogenation. I think this is molybdenum, not just M. This thing will react with acid in methanol. This N2 complex of molybdenum. And it makes some ammonia and some unknown stuff. Metal 6, molybdenum 6. That was a pretty early one. That got people excited. About 10 years later, not quite, my PhD advisor got tenure for this reaction. Sorry, 4, not 9. 1974. He made this CP star zirconium dichloride and reduced it with sodium and mercury. This is a pretty common way to get into N2 chemistry. He made this cool molecule here. Well, I should write it out. And when they first made it, they had a hell of a time getting a crystal structure of it. But they did have vibrational spectroscopy. And that's what they found. 2041, 2006, and 1556. 1556 is pretty darn low. What kind of a bond is that? More like a double bond. It's getting into single bond territory. Getting down there. What you thinking, William?
It's trying to move electrons around the left.
We didn't draw the, oh yeah. What's the oxidation state here? The N2s are just neutral to electron donors, right? CP ligands, however, 1x per CP. So both of these zirconia and zirconium-2. How many d electrons does zirconium-2 have? 2 d electrons. Would you say that's an electropositive metal? Yes, very. This is an extremely flammable substance that's very hard to isolate. This is you got to be a pro to do this kind of thing. Well, these compounds react, really want oxygen, really want to get rid of those hydrogens. So they're capable of reducing N2 down to give you these low frequency vibrational modes because of how electropositive they are. Okay.
It is the 2 N2s like that are bridging the zirconium, right? It's not the ones that are on it's not the terminal N2s that are.
No, that's right. This is the mu2 N2 here, this guy. Okay. This compound also reacts with HCl to make hydrazine. This beautiful compound. And you will get proteinalysis of hydrazine out. And so that's pretty consistent with that resonance depiction, isn't it? You're adding HCl across those 2 double bonds. You give 2 hydrogens on each nitrogen and 2 chlorines on each zirconium. And that's why this N2H4 pops out. So that all kind of adds up nicely. So this got Burkhardt tenure at Caltech. Another one, Kit Cummins. When I was in high school, Kit, I think, was like 23, professor at MIT, trying to get tenure. Something like that. Kit made these molybdenum compounds. You got 3 amido ligands here. How many electrons? How many valence? Or how many valence electrons are this molybdenum? How many d electrons does molybdenum have? 6. How many electrons for an NR2? 1 for each. There's also a lone pair here. So we could push electrons onto the molybdenum and raise its count that way if we wanted to. But if we just take the single bonded resonance depiction for a moment, you got 1 each. So 1, 2, 3, and 6 is 9. It's a pretty low number, right? That's a pretty frustrated metal. Super hypovalent. Super hypovalent metals are very reactive, particularly when made of these electropositive metals. And you can add N2 to this at minus 35 degrees Celsius. It forms this thing. And then it reacts with another MO and R3, sorry, NR2 thrice thing, and it makes this. And that goes on to two of these. This was pretty exciting thing at the time. So one N2 binds, another one comes along and sticks to it. You get this bridging thing, and it falls apart into two terminal nitridos. This was work done by an undergraduate, Catalina La Plaza. Undergraduate researcher did this, or at least made the initial observations. It was followed up by graduate students, but undergraduate is the first to do that. Catalina La Plaza went on to Harvard, worked for Dick Holm, and I don't know what happened to her after that. This got Kid Cummins tenure at MIT. He was the youngest person to be made full professor at MIT. I think when he started, yeah. I might be wrong about that, but yeah, it might be 25. It's pretty young. Prodigy, I don't know. You should listen to Kit give a lecture if you have a chance. Students should invite him to come here and give lectures to us. That's Moly 6. Nitrido through its 3 X-type interactions. Each one of those is an X-type. That's Moly 6. How many electrons for this compound? We already decided we had 9 over here, right? 1, 2, 3, 6. That's 9 electrons. And this guy is Moly 3. That's a D3 metal center. How many electrons now? Well, we still have the same Moly 3 thing there. And now you're getting 3 more electrons from that nitrido. So this is 12 electrons. Molybdenum 6, D0. Okay, so the 3 electrons on these molybdenums, each one went to N2. You need 6 electrons to break N2 into 2 nitridos. Each of the 3 came from these guys. All right. Dick Schrock, Paul Chirek, well, not Dick Schrock, but Paul Chirek got tenure for a similar type of reaction at Cornell. Jonas Peters got tenure at Caltech for another type of reaction. N2 after N2 after N2. It's like a test piece for inorganic chemists. Yeah.
Is like the process of like fixing nitrogen still like as researched and like as important, or are people looking at like different ways to fix nitrogen?
Yeah, for sure. Electrochemical reduction of N2 is a big deal. There's a lot of interest in that.
Is this type of like sort of fixing nitrogen with like through inorganic chemistry, maybe not through the electrochemical, maybe there's still research now? And if it's like,
Are there still coordination chemists working on it? For sure. Yeah. It's you know, it's one of the most important processes in the world, right? Like, the world's food supply has doubled because of it. And it consumes 1% of global power. That's a lot of CO2. So yeah, there's a big interest in it, especially because it's downhill and, you know, organisms do it at room temperature in the dirt. There must be a better way.
So the concern is really like the energy cost. If you can't slow population growth by just changing your mode of producing fertilizer, like population growth will continue to consume, right? So you're kind of like ignoring that, but just focusing on the energy part of it. That's why you're trying to find different ways to produce chemists.
Yeah.
They're trying to find different ways to produce fertilizer.
Yeah, I mean, you know, people like chemists who are researching things in the lab or trying out new stuff are just trying to make powerful tools. And the society does what they want with them. You know, blow somebody up or feed poor people or whatever you want, you know.
So we mentioned that like inorganic chemists look at this, electrochemists look at this, other biochemists trying to like
Sure.
hijack the organic process.
Absolutely. Yeah, I mean, it's still a topic of interest. Like the microorganism that does this has an iron sulfur cluster with a molybdenum on it. In the middle of it, there's a carbon atom bonded to 6 irons. It's like a really weird cluster to find in a natural thing. And so people have been trying to figure out how it works forever. Water oxidation is another one of those like life-sustaining reactions. Making dioxygen is a hugely important process. It's catalyzed by a manganese oxo cluster with some cobalt or something in it, or calcium. People want to understand how that works too. So yeah, that's contemporary. There's less and less tolerance for it though, because it's sort of regarded as like, you know, intellectual curiosity and less about real practical technology.
There's a lot of like thinking about how we can like basically like recycle human waste and like basically use our separated urine to like reproduce ammonia, so we're not like making more ammonia and just throwing it like down the drain in a sort of literal sense.
Huh. It's kind of gross.
Yeah, but it could be like life changing if you have like an entire like have that system set up in a building and use people as waste and ammonia to like grow
Yeah.
plants within the same building, then you're like
Right.
creating this.
Yeah, I mean, I guess I don't know the, be interesting to look at the energy balance there. I mean, the bottom line is that plants, you know, ammonia is basically gasoline for plants. And you can't just pull gasoline out of thin air. It's got to come from some energy source. So if urine is got a lot of energy in it, then that's good, I wonder, though. All right, so let's move. We're going to talk about arene complexes. And in particular, we're going to talk about cyclopentadianyl. CP is a great spectator. What does that mean? It means that it doesn't participate really. It's just sort of like caps the metal and stabilizes it and keeps it in solution if you want to do solution chemistry. It hangs on, hangs tough while other things are happening. Okay. It uses 3 coordination sites. This is an L2X. It's like half of an octahedron, or half of the ligands that form an octahedral center. Okay. It's a strong electron donor. Right, it's L2X, 5 electrons. It's also a weak delta acceptor. What does that mean? Delta acceptor. There's an empty orbital of delta symmetry. If you go from the middle of the ring down to the metal, you can have 2 nodal planes along that axis, and that makes a delta bond with the underlying transition metal. Which orbital would do that? Well, it's an acceptor, so it's the empty orbital. It's the next highest one in the series of MOs that define the 5 p orbitals, right? There's the totally symmetric one at the bottom. There's an E set with 1 node, and there's an E set with 2 nodes. The E set with 2 nodes has delta symmetry with respect to the underlying metal. So the LUMO is delta and it is a weak delta acceptor. All right, so you find stuff like metallocenes. These guys are pretty common. This CP iron is called ferrocene. It was one of the first compounds with a stable metal carbon bond isolated. It was isolated with a shovel. Did I tell you this already? Oil refineries produce cyclopentadiene. They produce dicyclopentadienide, actually, or dicyclopentadiene. And it falls apart and makes cyclopentadiene at about 150 degrees. And that reacts with the metal in the pumps at an oil refinery, and it makes ferrocene. And so they used to have to occasionally open up the pumps at the oil refinery and shovel out this orange powder they discovered was ferrocene. So ferrocene is one of the first metal carbon bonds that was stable, and it led to a huge amount of interest in organometallic chemistry. Nobody thought transition metals and carbon made stable complexes. And suddenly it was like crystallizing out of these pumps that were, because the pumps were getting hot. You know, that's totally surprising. Yeah.
So it was like reacting with the actual pipe itself.
Yeah.
And nothing, did that cause any issues down the line? Like, did anything like, did the pipes?
Yeah, it's corroding the pipes, basically. It's corroding the pumps, I think. Pumps would get real hot.
So
Yeah.
I'm just trying to think, like, I feel like that sounds like a disaster here. Working at we're fucking.
Yeah, well, people used to die in the chemical industry all the time. They still do, yeah. It's not as common. The safety is a big deal. They used in my hometown. Dow Chemical is in my hometown. My dad was a chemist there. I worked there in the summertime, and they used to electrolyze bromine, and there were all these salt deposits, brine wells essentially. So they pumped the salt out of the ground, they electrolyze it, and they made bromine and chlorine, and they sold chlorine. They started chlorinating hydrocarbons, and all of the like chlorinated biphenyls that are out there, you know, they come from Dow. And so they used to take chlorobenzene and they would convert it to phenol by heating it with sodium hydroxide. They did this at really high pressures in these pipes. The process is, I think it's still the same. And it was designed, eventually the pipes actually would just corrode from the inside out because they were full of hot concentrated sodium hydroxide to make this reaction happen. And they eventually would burst, and then they just replaced them. You know, so like the process was designed to continue running until the pipe blew up. You know, so it was like in a special box that was waiting for that to happen. So, you know, you get down to brass tacks of how stuff was made, and it's not always pretty. All right, iron. What's the oxidation state? 2 CPs on an iron. Iron 2, how many electrons for iron 2? 6. Iron 2, D6 octahedral, right? There it is again. That's why it's so dang stable. 18 electrons for an iron 2, D6 octahedral. Sounds about right. It's a low spin. Definitely low spin. CP is a strong field ligand. Okay, it's a strong donor. All right, you also find things like bent metallocenes. We have 2 CPs on a metal that has some other ligands on it. And you can have all kinds of stuff here. X can be hydride, it can be halide, it can be carbon monoxide, it can be phosphine, all kinds of things will fit in that spot.
What's written next to that?
N. And N is typically 1 to 3. So you have as many as 3 things. And this position of these compounds kind of look like that. You got a metal in the middle and 2 sandwich pieces of bread that are sort of tucked to the side. And the empty space on the other side here is called the wedge. Okay, so you can have as many as 3 things in the wedge. And you see these types of compounds on the left-hand side of the periodic table. So scandium to manganese. You don't typically see this on the right-hand side. And that's because 2 CP ligands, you're talking about 10 valence electrons, right? You can't really do that for a transition metal that has the electrons, so you're going to get beyond 18 real fast. Okay, so in a lot of places, one of the experiments kids do in synthetic chemistry lab is they make kerosene. One experiment. This compound here has a boiling point of 170 degrees. This is called dicyclopentadiene. It's the Diels-Alder product of 2 CPs reacting with each other. And it will do a retro Diels-Alder reaction at about 150 degrees. So it doesn't really boil. It decomposes. Okay. Decomposes to make 2 equivalents of cyclopentadiene. This compound has a boiling point of 42. So you just take a pot of this, you heat it up to about 150 degrees, and CP starts boiling out. And then you can collect CP and keep it cold and do chemistry with it. You can deprotonate it. And make cyclopentadienide out of it. The pKa of cyclopentadiene is 18. That's about the same thing. It's about the same as phenol. So that's pretty acidic. Propylene, that's another allylic CH. This is a doubly allylic CH here, right? So the double bond stabilizes the carbanion. Propylene's pKa is 44. And 1,4-pentadiene is 35. So 18 is quite a bit lower, right? I'll just put it up here. You get a 17 orders of magnitude change in the acidity just by taking 1,4-pentadiene and tying it into a ring. Okay, so resonance is real. CP is more acidic than ethanol. That's kind of cool. All right. So once you make a salt like that, you can do some chemistry with it. A salt. Once you make the cyclopentadienide anion, it's ready to do some chemistry with metal salts. This guy, you take 2 of these, mix it with an MX2. Make these. This is pretty successful kind of a reaction most of the time. Okay, so that's one standard method. Another is, we'll call this salt metathesis. Another sort of approach is CH activation. So you don't have to make those kinds of CP anions. You can just heat CP in an iron tube and it makes ferrocene, like at an oil refinery. That happens by CH activation. You can take iron pentacarbonyl and do that too if you want. You take 2 iron pentacarbonyls and 2 CPs. And you get the fifth dimer. What's missing? What are the other byproducts? Give me some balancing equation for me here. Okay. Some hydrogens. What do they do? What do the hydrogens do? They can make dihydrogen. Kind of cool. You can also take dimanganese decacarbonyl and react it with CP. And make this compound here. It's 4 COs. Again, spitting out H2. Oxidation state here. 1. How many d electrons? 6 d electrons. Probably it's 18 electrons overall, right? Because it's octahedral D6. 5, 7 is 12, 6 is 18. D6 octahedral, 18 electrons. Nice and stable. Okay. Let's take a look at the bonding in a metallocene. So we've said it's like octahedral, right? And it's typically low spin. off and D6. Okay. So these types of complexes have a E over, well, depending upon the geometry of the thing, it's going to be an A plus an E. These two are not going to be exactly the same in energy, but it's approximately like this. Okay. No, I got this wrong. I need to slow down here. That's not right. But you end up with something that looks approximately like that. We're going to do this a little more carefully. So you can think about CP compounds as being approximately octahedral, or metallicenes as being approximately octahedral. So let's take a look at the aromatic fragment first. Okay. So the frost circle trick. What's the frost circle trick? Frost circle trick allows you to draw an MO diagram for an aromatic system. You do so by putting the point of the shape you're drawing down. So like a cyclopropane, put the point down and draw one line for each of the carbons, right? So cyclopropenium, draw the point down and you get one level at each carbon. That's the MO splitting of an aromatic system. For cyclopropenium, cyclopentadianyl, looks like that. One level for each of the 5 carbons, and so on and so forth. Okay. This guy is A1. This is an E double prime and an E prime. Those are the labels. This one has 0 nodes. 1 node. 2 nodes. Right? As you go up, you add one more node. 0, 1, and 2. 0 nodes, 1 node. For benzene, it would be 0, 1, 2, 3 nodes. Let's draw these things out. How many nodes? 0. There is the one that's in the plane of the ring. Okay, but what we're thinking about now is the pi bonding resonance. Okay, so there's 0 nodes in the pi system. The next one has a node. So how do you draw that? Well, what you do is you pick an orientation where the node is lined up with one of the atoms. The molecule doesn't care where you draw the nodes. Okay, we're just going to pick a node along the atom to make our lives easy and make the drawing neat. And then the left-hand side of this node is going to be positive and the right-hand side is going to be negative. Okay. You can do the same thing for the other MO. This is a doubly degenerate situation. So what you do is you just redraw this now with the node at 90 degrees from the other one to make it orthogonal. So the top is going to be shaded and the bottom is not. And the closer you get to the node, the smaller the amplitude, closer to 0, right? So you draw the shapes that way. Let's do the next one. Pick along one atom. And then this is going to have alternating symmetry as you go around. That kind of looks like a d orbital, doesn't it? Same thing, 45 degrees. Alternating as you go around. Okay, so that's how you make MOs for aromatic systems. It's easy. It's very easy. 0, 1, 2, 3 nodes as you go up. That's all you gotta know. Pick the node along the atom. If you have a double degenerate one, rotate by 90 degrees if it's a single node, rotate by 45 degrees if it's a 2-node system, and then you just color it in. It's not that hard. You know, you just got to do it a few times. This thing, when sitting on a metal, makes a nice connection to dz squared. Dz squared orbital points right up at this guy and makes a nice connection. These two, there's a node along the metal. They fit very nicely. DXZ, DYZ. These guys are like pi symmetry orbitals, right? This is where the action happens. This MO is the HOMO. 6 electrons in cyclopentadianyl. This is the HOMO. So the donation from the CP ring is really driven by these guys here to this DXZ and DYZ pair. And what about that? What kind of symmetry is that? This is sigma, this is pi, this is delta. This is your delta accepting orbital. And it's the x squared minus y squared and the xy that make a connection to it. It's like an Oreo cookie, right? X squared minus y squared and xy are the frosting in the middle. And they have delta symmetry. Okay? Yeah, you can see the shape of them, exactly. Nodal planes along that axis from the CP centroid to the metal. Okay? You guys are pros, man. Look at that. It all makes sense now. It's awesome. All right, we'll just pick this up again and revisit it briefly when we start next time. So we'll see you on Wednesday.
Is our final lecture on Wednesday or next Monday?
I'm sorry, what?
Our final lecture is Wednesday or next Monday?
It's next Monday. Next Monday.
We have lecture on Wednesday and then the exam.
Exam is on Friday.
No lecture on Wednesday.
No lecture on Wednesday.
And problems that do this year.
Got multiple things happening at the same time here. We're going to stick to this class schedule. So the last lecture in this class will be Monday of next week. Final exam is Friday of that week. Problem set is due on Wednesday.
Time for the final exam, I think we got 2 different times emailed. Is it 2 options or just the one?
We have decided to schedule the exam from 10 o'clock to 1 o'clock in here. Is that right? Yeah, 10 to 1 is the time frame.
Okay, great.
Yeah? Should I send another follow-up? Is there confusion about it?
There was just an earlier email with 2 time slots.
Yeah, I
and
was
then
asking which one anybody
Gotcha.
wanted to rule out.
Gotcha.
Yeah.
I changed the tentative meeting schedule. I'll talk to Natalie about it.
Okay, thank you.